Hello friends, today's topic for discussion is alkyl halides and nucleophilic substitution reactions. Now, alkyl halides are extremely important reagents in organic synthesis because of the presence of the halide, negatively charged halide ions here. Okay, they are weak bases. Now, the substitution reactions, we can say they are characteristic reactions of organic molecules, organic compounds containing a C-set sigma bond. You know that C-set sigma bond here. That means the substitution reactions are characteristic reactions of organic compounds containing a C-set sigma bond, where set is sigma bond here. Okay, set, it is an atom. It is more electronegative than carbon atom here. Therefore, the carbon atom becomes partially positive. Okay, so it will become an electrophilic center, electrophilic site, that is electron deficient site here. So I will explain it with the help of this halides, alkyl halides here. Alkyl halides is generally we are writing here RX. R is an alkyl group here. It can be a methyl group, it can be an ethyl group, propyl group, and all these kind of things here. Okay, so this will contain a carbon atom here. So this carbon atom, the most important point here which we will have to see it is this carbon atom will be sp3 hybridized carbon atom. Okay, and this one, okay, this is the halide anion. Basically set is a halide, mostly it is a halide here. That is halide will be fluorine, then you have your chlorine, bromine, iodine. Okay, this is more, these are the important groups here. Negatively charged anions it will be forming here. So X will be CX. Here this carbon, it is an sp3 hybridized carbon atom here. Okay, alkyl halides, they contain a halogen atom, and it is halogen atom, it is bonded to an sp3 hybridized carbon atom here. Now alkyl halides are different types. That is primary, secondary, tertiary, etc. Just like primary carbon, secondary carbon, tertiary carbon, or primary hydrogen, secondary hydrogen, tertiary hydrogen, and all these kind of things here. So alkyl halides, they are classified as a primary. That is what is meant by the primary. Primary means it is only one this thing will be there here. Okay, so this will be a primary. This one R, say we can say RCH2X. This is an alkyl halide, primary alkyl halide here. Okay, therefore this carbon atom, it is bonded to one R group here and two hydrogens and the halide group RCH2X here. Then we can have two R2CHX. Correct. So this primary we call it 1 degree we write here, and this is secondary 2 degrees R2CHX here. Then we can have tertiary, that is R3CX. So this is a 3 degrees. Okay, this is tertiary. This is the classification of alkyl halides. We have primary, secondary, and tertiary alkyl halides are here. Okay, it depends upon the number of carbons bonded to the carbon atoms bonded to the carbon with the halogen. That is the thing. You see, we have a carbon atom bonded to the halogen atom here, and the other one. That is it depends upon the number of the carbon atoms bonded to the carbon with the halogen atom here. Okay, that is how it is classified here. That is primary, secondary, and tertiary, and all this kind of a thing. Now, an alkyl halide, whether it is a primary alkyl halide or a secondary alkyl halide or a tertiary alkyl halide, this is the most important factor here. Most important factor determining the course of a chemical reaction. Okay, the course of a chemical reaction depends upon what type of alkyl halide it is, whether it is a primary one or secondary one or a tertiary one here. Now these examples and all, I can just show you so many examples we can write here like this, CH3, say CH2. So then we can have, say CH2I. So this is a primary alkyl halide here. So now a secondary alkyl halide. So if you write, see, this is the secondary one. This is a 1 degree. This is 2 degrees. That is primary, secondary. Then tertiary. tertiary will be how it will be, say CH3, say CH2, say CH3, say Cl, chlorine, say CH2, CH3, etc., etc., whatever it is there. So this is the tertiary. This carbon is a tertiary carbon here. Therefore, it's a tertiary alkyl halide. That is, this reactivity depends upon this primary, secondary, and tertiary. So I am just giving a brief introduction about the alkyl halides here before going into the nucleophilic substitution reactions here. Now, suppose we are having a compound like this. What will be the situation? So, this compound. What is this? So this is CH2 double bond CH X. This is this compound here. This is a vinyl halide. Okay, this is not an sp3 hybridized carbon atom. Therefore, it will not give you a nucleophilic substitution just like other alkyl halides here. Okay, carbon should be an sp3 hybridized carbon. So this is the vinyl halide. Then I can give you another example here. This is the aryl one. So this will be X, aryl halide. This is also not an sp3 hybridized carbon atom here. Okay, so these things doesn't give the nucleophilic substitution reaction just like the other alkyl halides, because in both the cases here, the carbon atom it is sp2 and not sp3. Okay, this is the most important point here. Now suppose we are having a compound like this now. What is this compound? This will be very interesting. This is allylic halide. So here in this case, allylic halide. Allylic halide. So this carbon, particular carbon here, this carbon is sp3. Correct? Allylic halide. In the same way, say we can say this compound here. Now, see, like this, if we are having it's a benzylic halide. Okay, so this carbon here, this is an sp3 hybridized carbon atom here. So these are the difference here. So these compounds will take part in the nucleophilic substitution reactions here, etc. here now. Okay, just like any other alkyl halides here, because the carbon atom should be an sp3 hybridized carbon atom here. Allylic and benzylic and all having an sp3 hybridized carbon atom here. Now the chemistry of alkyl halides, it determines by the polar, polar bond. This bond, it will be CX bond here. This is the polar bond here. Okay, because it is created by how it has become polar, because this is a delta partially positive here and this will be partially negative because of the electron negative halogen atom here. Alkyl halide, the halogen atom, determines the polarity here. Okay, that means this polar CX bond. It is a polar CX bond. It is created by the electronegative halogen atom here. Okay, therefore, the carbon atom, it is made electron deficient. This becoming electron deficient carbon atom. That is, it will become act like an electrophile. Nucleophile, electrophile. Okay, electrophilic carbon. That is electron deficient carbon because of the presence of the halogen atom here. Okay, electron deficient. Therefore, the characteristic reactions of alkyl halide is substitution and elimination reactions here. Substitution and elimination reaction, because alkyl halide contains an electrophilic carbon atom. Okay, so it will react with what? Electron rich species. That is, an electron poor species, it will react with an electron rich species here. That is why this nucleophilic substitution. Why nucleophilic substitution means it involves the nucleophiles, electron rich nucleophiles here, because the carbon atom is rendered electron deficient. It has become an electrophilic carbon because of the presence of the halide anions here. That is the chemistry. Okay, of the alkyl halides here, CX bond, polar CX bond, simply remember that thing here. Okay, now, now let us see what are these electron rich and electron poor and all these kind of a thing. In the previous 1 or 2 videos I have released, where we have been discussing the Lewis acid base reactions. These substitution reactions, they are simply Lewis acid base reactions here. Okay, electron rich reagents means the Lewis bases. They are nucleophiles. We know electron rich bases, that is the Lewis bases. We have seen that thing. What is the Lewis bases? Lewis bases are nucleophiles. Okay, and Bronsted-Lowry bases. I will just briefly tell you what are these things. Bronsted-Lowry bases. Okay, therefore, now because of this alkyl halides, contains an electrophilic carbon atom, they react with electron-rich reagents. Electron-rich reagents, which are the electron-rich reagents? They are Lewis bases. They are acting as a nucleophile and a Bronsted-Lowry bases. Okay, therefore, now alkyl halides, I will explain these Lewis bases and Bronsted-Lowry bases briefly. So alkyl halides, they will undergo substitution reactions with the nucleophiles. So the reaction, I can just roughly I can show you. This is how the reaction take place here. So Nu minus, not necessarily should be minus, negative charge need not necessarily be there. So this is the nucleophile here. So this is called a Rx. This is the alkyl halide here. In the reaction, this Rx bond is broken. This is the sigma bond here. This sigma bond, it is broken here. Then this nucleophile will attack here, RNU. We will be getting a new bond here. Okay, then there is a group. This is called a leaving group. I will discuss this thing in detail. X minus, that is electron rich nucleophile. This is reacting with an electron rich nucleophile, and this is the nature of the reaction here, substitution reaction here. Okay, now let us see the alkyl halide. This is the substitution reaction here. Then the next reaction, it will be with the base. This is actually with a nucleophile. Okay, with a nucleophile, this substitution reaction here, and with a base, we get an elimination reaction here. Alkyl halides undergo elimination reactions with the Bronsted-Lowry bases. Okay, these are the characteristic reactions here of the alkyl halides. So, which is the the reaction will proceed. So, this will be reacting with a base here. Okay, this is the Bronsted-Lowry base, B. B, we are just showing here. So there will be an elimination reaction here. This HX will go here. So this will be getting a pi bond here. Okay, so then we will be getting, say, HB plus and all sorts of kind of things here. Okay, then X minus here. Okay, this is the what you call alkyl halide. They undergo elimination reactions like this here. Now, before this, all these things called, I just want to give you a brief introduction of the Lewis bases and Lewis Bronsted-Lowry bases, which of course we have seen it in the previous class here. Now, briefly, I can say the Bronsted-Lowry acid and Bronsted-Lowry base. Bronsted-Lowry acid, that is the theory. It is based on the proton. Concept of protons here, proton transfer reactions. That is an acid-base reaction. That is a reaction between a Bronsted-Lowry acid and a Bronsted-Lowry base. It is an acid-base reaction. That is a proton transfer reaction here. That is why it is base. Base has got affinity for protons here, and a nucleophile has got affinity for an electrophilic center here. That is the difference here. We will discuss now. A Bl, in short, that is a Bronsted-Lowry acid. It is a proton donor. Okay, that means the structure it should contain a proton here. We know that HCl, H2, SO4 and so many acids are here. Of course, they are all Bronsted-Lowry acids here. Now, Bronsted-Lowry base, it is a proton acceptor. Okay, the theory is based on protons. Therefore, proton donor, proton acceptor. That is, for accepting a proton, a Bronsted-Lowry base, it should contain electrons. It should be an electron-rich species here. For a proton acceptor, for accepting a proton, it should be electron rich. Correct. It should have a lone pair of electrons or it should have a pi bond. Lone pair or pi bond. Okay, this is the characteristic feature of a Bronsted-Lowry base. Okay, it's a proton acceptor. That is, should contain a lone pair or a pi bond. Now, Lewis acid and Lewis base. So, Lewis acid means electron pair acceptor. Here, Bronsted is acid and bases are concerned with the protons, proton donating and proton accepting. Whereas in the case of Lewis acid and bases, Lewis acid is a electron pair acceptor. Okay, so for accepting an electron pair, it should contain a proton or an unfilled valence electron, valence shell, unfilled valence shell, not an octet here. Okay, or a partial positive charge. These are the three conditions here. For a Lewis acid, it is an electron pair acceptor, correct? Electron pair acceptor. So for accepting an electron pair, the structural feature, it should contain a proton or an unfilled valence shell, not an octet here, okay, or a partial positive charge. Okay, now Lewis base. Okay, Lewis base means it contains an electron pair donor. For donating an electron pair, it should contain a lone pair or a pi bond. These are simple things here which we have discussed, correct? Therefore, Lewis acid and bases here. So this is actually the nucleophilic substitution reaction we are going to discuss. Mostly these are all Lewis acid base reactions here. Now, what are the general features of a nucleophilic substitution reactions here? There are three components. Okay, so let us see. We will examine which are the three important factors or components of a reaction here. General features of a nucleophilic substitution reaction. So, you see, we are having a reaction like this here, Rx. Okay, this R, it contains a carbon atom here. This R, alkyl group, it will contain a carbon which is sp3 hybridized. Correct. Now, this Rx, it will be reacting with a nucleophile here. Okay, nucleophile, electron-rich nucleophile. That's why I'm just showing a negative charge over there. Okay, not necessarily it should be there. Nucleophile. Okay, so the reaction will be RNU plus X minus. So this X minus, it is known as a leaving group. Okay, R, it is an alkyl group. This is an alkyl group containing a carbon atom which is an sp3 hybridized carbon atom, and it's reacting with an electron-rich nucleophile here, forming the compound, and X minus. That X minus is known as a leaving group here. Okay, so this X, it can be a single atom or it can be a group of atoms here. Okay, not necessarily it should be a single atom. It can be a single atom or it can be a group of atoms. Leaving group, this thing is, what is happening here? There is a heterolytic cleavage here. That is, Rx bond is heterolytically cleaved. Heterolytic cleavage of the Rx bond here. Okay, so when the heterolytic cleavage is taking place, the electrons in the bond, Rx bond here, it is unequally divided. That is, R will not get anything. Entire electron will go to the X here. Okay, X should be able to take the electrons here. That is most important thing here. Okay, the leaving group X, it should be in a position to accept the electron density in the bond, CX bond or Rx bond, whatever it is there. Rx bond or CX bond here. We can say this CX bond because R contains a carbon atom which is sp3 hybridized. Therefore, there is a CX bond here. This CX bond, it is getting heterolytically cleaved. That means the electron pairs forming the bond, it is unequally shared, unequally divided. Carbon here doesn't get anything and entire thing will be taken by the more electron-negative X here. Therefore, carbon will become positive and X will become negative here. That means X is the leaving group here. X minus is the leaving group here. So the leaving group, it should be able to accept the electron density in the CX bond. That is a capability. Okay, the characteristic feature of the leaving group we will discuss now. So nucleophile, the nucleophile, it will contain a lone pair of electrons or a pi bond here. Okay, it's not necessarily a negative charge. It should contain a lone pair or a pi bond here. So this is the nucleophilic substitution, because these substitutions reactions, they involve electron-rich nucleophiles. That is why it is nucleophilic substitution here. Electron-rich nucleophiles are there. Either there is a lone pair or there is a pi bond here. Okay, now these are basically Lewis acid-base reactions. Correct. These are basically Lewis acid-base reactions here. Now the alkyl halide here. Okay, alkyl halide is the Lewis acid. Okay, alkyl halide, it is the Lewis acid, and it will accept the electron pair here. Okay, because Lewis acids are electron pair acceptors, we have seen that now. So alkyl halide acts as the Lewis acid. It will accept the electron pair. It is donated by the nucleophile here, because nucleophile is an electron-rich species. Therefore, it is donating the electron pair, which the alkyl halide is accepting. So electron acceptor, that is the acid. Alkyl halide acts as the Lewis acid here. Now the bond cleavage, CX bond, it is heterolytically cleaved here. The electron pair, it is taken by the X group here, halogen group here. Alkyl halide, that is halogen atoms. So it is a Lewis acid. It will accept the electron pair donated by the nucleophile here, and the CX bond is heterolytically cleaved here. Okay, now simple example, I can just give you, that is a methyl chloride. So a compound like this now, say CH3Cl. This is the simplest methyl chloride here. Then we can say an OH minus. Okay, this is the nucleophile here. So this is giving you the methyl alcohol. Methyl alcohol. Then we have the chlorine minus, Cl minus. This is the leaving group here, and this is the nucleophile here. Okay, so this is how the reaction take place here. Okay, now another example, say CH3, CH2, say CH2, iodide anion, iodide. It is giving you, or it is reacting with what? Nucleophile should be there. Okay, so the reaction, we can SH minus. Okay, is a nucleophile here. Okay, so this will give you a compound CH3, CH2, CH2, SH. Correct? Plus I minus. So I minus, it is a leaving group here. Okay, so like this, we can have nucleophiles, and we can have the alkyl halides, and we can have the leaving group here, alkyl group here. Then there will be a nucleophile, and there will be a leaving group. Okay, leaving group. So here, the Cl minus, I minus, they are all leaving groups here. Okay, so here the negatively charged nucleophile, like this OH minus, SH minus, etc. They can be used as a salt, with lithium, say sodium, potassium, and all this kind of a thing. We can use it. Used as a salt here. Now, when a neutral species, say neutral nucleophile is there. Here all we are talking about the negatively charged one. So a neutral nucleophile, say CH3, say CH2. This is an alkyl halide here, bromine. So this is reacting with a neutral nucleophile. This is okay. Neutral nucleophile. What will happen? See this. Correct. So this will react like this, CH3. Then we get a positively charged N plus CH3 thrice. Okay, plus Br minus. So this Br minus, it is a leaving group here. That is a neutral nucleophile. When it is used here, the substitution product bears a positive charge. Okay, now if you use excess of this material here, again it will be a neutral molecule. Say a simple example, we can show, say, CH3, CH2, CH2Br. Okay, so this is reacting with ammonia. What will be the nature of the product here? So this is reacting, that is the reaction will proceed in 2 steps here. That is ammonia, we are using excess of ammonia. Therefore, the final product will be a neutral product here. Okay, so this will give you a compound, this. So this will go here, this lone pair, this is the attack here, electrophilic site here. Okay, so the compound formed will be CH2, then we have NH3. Okay, there is a positive charge here, correct? So this will again react with excess of ammonia. So what will be the type of the product formed here? Excess ammonia. This is a step 2, and this is the step 1 reaction here. So there will be a proton transfer reaction. So this proton can be transferred. Okay, so when this proton can be transferred here, so in the next step, the product formed will be NH2. This is amine. It's an amine compound is formed here. Then we get NH4 plus. That is the reaction taking place in excess of ammonia here. So the neutral product, this is the neutral product here, and this is the positively charged NH4 plus here. See, all of these reactions, they are nucleophilic substitution reactions, we can say, correct? All of these reactions are nucleophilic substitution reactions, correct? Now, whatever may be the type of reaction here, whether it takes place in step 1 or step 2 here, finally what is happening here, it is replacing the replacement of the leaving group by the nucleophile here, correct? The leaving group, it goes with the electron pair, and the nucleophile, it is getting substituted by the nucleophile here. Okay, now what is this leaving group? We have been talking about leaving group. What should be the characteristic of this leaving group here? It's a very important point. So I will briefly tell you leaving group. See, in a nucleophilic substitution reaction, say Rx, correct? The CX bond, we know that it is heterolytically cleaved here. Rx is R is an alkyl group containing a carbon atom which is sp3 hybridized here. So here the CX bond, it is heterolytically cleaved, and the leaving group, it departs, okay, with the electron pair. That is the electron pair or the electron density in the CX bond. When the heterolytic cleavage take place, the leaving group, it will leave with the electron pair. It will depart with the electron pair in that bond, forming this group here. We have seen this is the leaving group here. Okay, the electron pair is taken away by this group here. Correct. The more stable, now everything depends upon the stability of this X, the species X here. Correct. So the more stable the leaving group it is, the better it is able to accept the electron pair here. Correct. The stability of the leaving group, it should accept the electron pair. When the bond is heterolytically cleaved, it has to depart with the electron pair here. Therefore, after getting this electron pair, it should be a more stable species here. Okay, the more stable the leaving group, it is, the better it is able to accept the electron pair here. Okay, got the point? Now, when you are given the leaving group, two leaving groups you are given, you will have to compare which is a better leaving group here. Okay, we call it a better leaving group. In a reaction, which is a better leaving group. So this is used to find out, whether the reaction will proceed in the forward direction or in the reverse direction, whether it will favor the formation of the products or the reactants and all. We can see by seeing the better leaving group, which is the better leaving group here. Now we can say nucleophilic substitution, it will occur with the leaving group that are weak bases. Most important point here, weak bases. Leaving groups are all weak bases. It should be a weak base. Okay, so in this kind of a reaction, Rx we have seen. So this electron pair it is taken away by this leaving group when it is reacting with a nucleophile here. Okay, this is giving RNu, not nitrogen, this is Nu. Okay, plus X minus. This is the reaction here. Okay, the nucleophilic substitution occurs with the leaving group that are weak bases. The X minus, it should be a weak base here, because then only it will be stable here. Now, let us see. So water, we can just compare, say water, the H2O, then OH minus. Two things. Right, which is a better leaving group here? So water is a better leaving group than OH minus, because water is a weaker base. Correct. So this will be water is a weaker base. This is the comparison. This is how we have to compare. Water is a weaker base and OH minus is a stronger base. Therefore, better leaving group is always a weaker base. Correct. Now, what will decide which is a weaker base and which is a stronger base, etc. Then we come to the concept of the conjugate acid. We have seen in the acid-base reactions and all, conjugate acids and conjugate bases. Okay, the acidity of various compounds are compared using the pKa values. We have seen conjugate acids and conjugate bases. That is, we have seen the acidity and basicity are compared using the pKa values here. That is, pKa means the smaller the pKa value, the stronger will be the acid. Now the basicity is compared using the pKa values of the conjugate acids. Correct. So this is how we have to determine here. So here water, it is a weaker base and OH minus is a stronger base. A weaker base, it will have a strong conjugate acid, and a stronger base will have a weak conjugate acid here. We determine it all using the pKa values here. Okay, now in the periodic table, if you see the periodic trends of acidity and basicity, we have seen that is from left to right across a row of the periodic table, that is a period, and we have the periods and we have the columns there. So from left to right, if you move, we have seen the acidity increases because the electron negativity increases here. That we have seen. So when the acidity increases, the basicity decreases. Okay, left to right across a row of the periodic table, basicity decreases. Okay, so when the basicity decreases means the leaving group ability increases, because leaving groups are always weak bases. We have seen that, no? So, leaving groups are always a weak basis. Okay, now when we are moving from now ammonia, we have ammonia and we have water. Okay, two nucleophiles here. So ammonia and water in the periodic table, if you see now this side, if you move from this side here, what happens? From left to right across a row of the periodic table, the basicity it will decrease. So this side, right to left, the basicity increases here. Correct, increasing basicity. So increasing basicity means decreasing leaving group ability. Correct. So increasing basicity, water is less basic compared to ammonia, or ammonia is more basic compared to water here. Left to right across the periodic table, basicity decreases left to right. Okay, therefore the leaving group ability increases. Now right to left, we are seeing here water and ammonia, that is the increasing basicity. Then this side, if you see like this, it will be increasing leaving group ability. Increasing leaving group ability here. Okay, these are second row elements here. Second row element, water, H2O, oxygen and ammonia. Second row elements here. Okay, now increasing basicity, right to left we have written here, and left to right it will be increasing leaving group ability. Okay, as the basicity decreases, the leaving group ability increases. Correct? Now this is across the column, across a row of the periodic table. Now if you come down down a column of the periodic table, how it will be? Now a column of the periodic table, which are the elements here? Now we have the fluorine, then we have chlorine, then bromine, iodine here. Okay, what will be the trend here? Down a column of the periodic table, the basicity decreases. Therefore, the leaving group ability increases. So down a column like this, if you see down a column. Now, okay, here down a column of the periodic table, the basicity increases. Correct? Therefore, leaving group ability basicity decreases means the leaving group ability increases. Okay, this is the down a column of the periodic table. The basicity will decrease. That is, iodine, it is the least basic iodide is the least basic species here. Therefore, iodide anion, it will be the best leaving group here. Okay, down a column of the periodic table. Okay, the basicity decreases, so the leaving group ability will increase here. Okay, now iodide, it is the weakest base here. Iodide anion, it is the weakest base. Therefore, it is the best leaving group of this series. The best leaving group, it is the iodide anion here. Okay, now all very good leaving groups, they are weak bases. That is the most important points here. Okay, they are weak bases here. Or good leaving groups are weak bases. Okay, and when the base is a weak base, a strong conjugate acid. Strong conjugate acid means low pKa value. Okay, so very good leaving groups, they are all weak bases, and weak bases will have a strong conjugate acid, and strong conjugate acid will have a low pKa value here. Therefore, all halide anions here, except fluorine, we can say they are good leaving groups here because their conjugate acids have low pKa values here. Okay, now the leaving group. A leaving group, it can be a single atom or it can be a group of atoms. Okay, maybe it can be a negative ion, or it can be a neutral species. There is no hard and fast rule here. Okay, it can be a single atom or it can be a group of atoms, or it can have a negative charge or it can be a neutral species here. So the leaving group, it is more electronegative than the carbon atom. That is the only thing which we'll have to see here. When you are having a CX bond here, heterolytic cleavage, electronegativity factor, if you see, the leaving group, it is more electronegative than the carbon atom to which it is bonded. Okay, and when the bond breaks, the bonding electron pair, it remains with the leaving group here. Okay, now typical atoms of the leaving group. Which are the typical atoms? We have this oxygen, so then we have this nitrogen, then we have sulfur, halogens, and all these kind of things. You see, they are all the typical atoms of the leaving groups here. Correct? So this can be a single atom leaving group, or it can be a group of atoms here. Okay, it can be as a single atom or a group of atoms, or it can be a negative species, or it can be a neutral species. Okay, it should be more electronegative than the carbon atom to which it is bonded. That is more important point here. Okay, therefore when the bond is breaking, the CS bond is heterolytically breaking, the electron pair remains with the leaving group here. Correct? So this is all the fundamental introduction to the leaving group. Now let us see the good leaving groups and poor leaving groups here. I'll just give you a brief introduction. Which are the good leaving groups and which are the poor leaving groups and all this kind of a thing, different kind of classification, why it is a good one and why it is a poor one. So good leaving groups, I will simply write in short LG, leaving group. Say if you have a starting material, say RCl, chlorine, the leaving group here, it will be chloride minus. What is the conjugate acid? This is a leaving group. This is a starting material. Starting material is RCl. The leaving group is chloride anion. Then which is the conjugate acid here? HCl. It is the conjugate acid here. What is the pKa value? pKa value is -7. Okay, this you can get from the tables here. So the next will be your RBr, bromide. So bromide minus. This is the leaving group here. Conjugate acid is HBr. HBr is, I think it is -9 or something like that. Okay. Then we have Ri. Okay. The leaving group here is the iodide anion. So Hi. So this is the strongest one here, -10. That is the lowest pKa value here. So we get a strong, that is a conjugate acid here. Now if we come to ROH2 plus, correct, ROH2 plus, the leaving group is water, H2O. ROH2 plus leaving group, it is H2O, a neutral species. Now the conjugate acid is the hydronium ion here. So the hydronium ion pKa value is -1.7 here. Therefore that is the lowest, the strongest acid here because of the pKa value here. Okay. So ions that are strong, we can say bases, they are poor leaving groups. Strong bases are poor leaving groups here. Correct. Now, the leaving groups, we can say they are not stable in the sense that, they do not want to be alone, we can say. So, these leaving groups, if a proton is present, for example, correct. So these anions will react with the protons there. That is the thing here. That is the, if a proton is present in the, in the system, in the reaction mixture, whatever it is there, these anions, leaving group anions, it will react with that anion. So if a carbocation is present, the anions also want to react with it, carbocations here. So these are the leaving groups, good leaving groups and poor leaving groups and all this kind of a thing, Now, let us see which are the starting material. If it is a F fluorine, here the leaving group is F minus here, HF. This is our conjugate acid. So pKa value is 3.2. Like this, there are so many this thing. A particular nucleophile and a leaving group. We can determine which will be a what you call a better leaving group and this thing, looking at the pKa values here. So different pKa values of the conjugate acids. So the stronger the leaving group, rather the base, we can say, because leaving groups are all weak bases here. Okay, weak bases. Weak bases will form strong conjugate acids. Correct. Now, if you are given a particular nucleophile and a leaving group here, so how will you determine whether the equilibrium, it will favor the formation of the products in the nucleophilic substitution? Correct. Now we can predict the direction of the equilibrium using the pKa values of the conjugate acids there. Correct. So how will you do that? Comparing the basicity of the nucleophiles and the in the leaving groups here, because leaving groups are bases. So how will you compare the strength of the leaving group here, looking at the pKa values of the conjugate acids here? So whether the equilibrium favors the products or whether it will favor the reactants or not, all this kind of a thing here. Okay, so now equilibrium will favor the formation of the products in a nucleophilic substitution when the leaving group, it is a weaker base compared to the nucleophile. Okay, when the leaving group, it is a weaker base compared to the nucleophile, the reaction will favor the formation of the products. The equilibrium will favor the formation of the products here. Now I'll just give you a question here. Tell me which one, whether it will favor the formation of the products or not here. So we have a reaction like this, CH3 CH2Cl, simple example. Okay, so this is reacting with OH minus nucleophile. So this is giving you a compound. Okay, now we have to see whether this reaction will proceed in the forward direction or in the reverse direction. Whether it will form, favor the formation of the products here. How will you see that? Now, compare the basicity of the nucleophile OH and the leaving group here. So, which is the leaving group here? The leaving group Lg is Cl minus, and nucleophile, it is OH minus. So, now you compare the basicity. Okay, compare the basicity of the nucleophile OH minus and the leaving group Cl minus by comparing the pKa values of the conjugate acids here. Now the pKa value of the leaving group Cl minus here, what is that? It is the conjugate acid is HCl. pKa value we can find out. So HCl is pKa. It is minus, I think it is minus 7. Okay. Now Nu, the nucleophile OH minus. So the conjugate acid here, it is water. Okay, pKa value, it is around 15, approximately 15, I think. Yeah. So now in this case, which is a stronger base and a weaker base here, we can see, because now Cl minus, that is a chloride anion, the leaving group. Okay, it is a weaker base here compared to the OH minus, the nucleophile, because the pKa value is lower the pKa value, the stronger the conjugate acid. So stronger the conjugate acid, the weaker the conjugate base. So a weak conjugate base will give you a strong conjugate acid here. Okay, strong conjugate acid will have a lower pKa value here. Now if you compare the pKa values of water, H2O and HCl here, we see HCl is a stronger acid. Therefore, Cl minus is a weaker base compared to the nucleophile OH minus here. Therefore, in an equilibrium reaction, the reaction will favor the formation of the products provided the leaving group, it is a weaker base here. Correct? So, Cl minus, it is a leaving group, it is a weaker base. Okay, compared to OH minus. Therefore, the reaction, it will favor the formation of the products here. Okay, so this is all about what you call the leaving group briefly. Now, the most important point here, we are talking about, all along we have been talking about nucleophilic substitution. So, I didn't tell you what is this nucleophile. Correct? So, briefly, what is a nucleophile? So, nucleophile means a Lewis base. We know that. Correct. Nucleophiles are, it means a Lewis base, and that reacts with an electrophilic site here. Okay, other than a proton. That is the thing. Because the base will react with a proton. Base will take a proton, and nucleophiles will take an electrophilic carbon. That is the difference here. Okay, nucleophiles, they are Lewis bases. So Lewis bases means it will have a lone pair or a pi bond. Okay, so this will react with electrophilic sites, electrophiles, other than a proton here. Okay, now base means, what is a base? Lewis base, and base means Bronsted base. Lewis base we are telling here, if you simply say base, it implies Bronsted base. They are Bronsted acid, they are proton donors. Bronsted bases are proton acceptors, we know that. So nucleophile files are Lewis bases, that reacts with an electrophilic site other than a proton. Okay, now the base means, Bronsted-Lowry base here. Now nucleophiles and bases, they are structurally similar. Okay, nucleophiles and bases, if you see the structure, they are similar here. Both have a lone pair electrons, or both have a pi bond. Correct? Only the difference is, they differ only in what they attack. Okay, the bases attack protons, whereas the nucleophiles attack other electrophilic centers. That means other electron deficient atoms, usually a carbon atom, we can say. So here, if you see, this is the difference between a nucleophile and a base here. Correct? Both are structurally similar. There is no difference here. Now, if you have this base will take this proton. Okay. Now, if we have so there is, if there is a reacting with a nucleophile here, so this lone pair, it will be it will attack this electron deficient carbon atom here. Okay, that is, this is the electron deficient carbon. This is the only difference here. Okay, so nucleophiles are Lewis bases. Okay, that will readily react with the electrophilic carbon other than a proton. Okay, now base means it is a Bronsted-Lowry base. Okay, now nucleophiles and bases, the structurally they are all similar kind of thing. Okay, now both will have a lone pair or non-bonding pair of electrons or a pi bond. Both will have a lone pair of electrons or a pi bond here. Okay, then what is the difference here between these two? That is the thing here, what they attack. Okay, the difference is only in what they attack here. Bases attack protons. Correct? The nucleophiles attack other electron deficient atoms, other electron deficient sites, electrophilic sites here. Okay, now nucleophilicity, there is a word called nucleophilicity. What is that? And basicity. So nucleophilicity means the strength of the nucleophile. That is a simple thing. Basicity means the strength of the base here. Okay, now the strong base, it is a strong nucleophile. Strong base means strong nucleophile. So it is generally true. It is only a general statement. Strong bases, they are all strong nucleophiles. But always it need not necessarily be correct. Strong bases equal to strong nucleophiles. General true, this thing. There are exceptions here. Exceptions will be on account of 2-3 factors here, which I will be just discuss now. The general thing is, generally we can say all strong bases, they are strong nucleophiles. So, but it can change. It need not necessarily be correct all the time. So it will depend upon the size of the nucleophile and certain steric factors. Okay, so depending upon circumstances, one is size of the nucleophile, it will influence. I will discuss only 2-3 factors now, rest of the thing in the remaining class. Okay, so size of the nucleophile, then steric factor. These are the two things which we'll have to understand here. Okay, because the strong bases are usually strong nucleophiles, usually, correct? But it can change depending upon the size of the nucleophile and certain steric factors. Now, for two nucleophiles with the same nucleophilic atom, two nucleophiles with the same nucleophilic atom, the stronger base, it is a stronger nucleophile. That is the first principle. That is, suppose we have two nucleophiles here. Okay, with the same nucleophilic atom. Nucleophilic atoms are, we have seen, nitrogen, oxygen, halogens, and all these kind of thing. Okay, two nucleophiles with the same nucleophilic atoms are there. Same nucleophilic atom means the stronger base will be the stronger nucleophile. First principle, that is, say, for example, two nucleophiles, say one is CH3COO minus, acetate anion, oxygen. This is an oxygen nucleophile, we can say. Okay, now there is a, this acetate anion, and another one is a OH anion here. Okay, now which will be more basic? Relative nucleophilicity. Let us see which is the relatively more nucleophilic here. Okay, now it is determined by comparing the pKa values of the conjugate acids, which we have seen now. Now the conjugate acids of OH minus, it is water, and acetate anion, the conjugate acid is acetic acid here. Now which is more acidic? What is the pKa value? pKa value of acetic acid will be, I think it is 4.8 here. This is the pKa value. Okay, now in the case of water, pKa value is around 15. Okay, now here the stronger acid, it is the pKa value 4.8, lower the pKa value, the stronger acid. Therefore, acetic acid, it is a stronger acid compared to H2O here. Correct. Therefore, OH minus, it is a stronger base. Therefore, a stronger base and a stronger nucleophile compared to CH3COO minus, acetate anion. That means two nucleophiles having the same nucleophilic atoms here. Okay, now we can compare it. In that case, what happened? The stronger base, it will become the stronger nucleophile. Correct? Now which we are finding out using the pKa values of, comparing the pKa values of the conjugate acids here. Okay, now OH minus here, it is a stronger base and a stronger nucleophile. It is a stronger base and stronger nucleophile. Okay, so now this is the first principle. Correct. Now a negatively charged. Now the second principle, we can say a negatively charged nucleophile, it is always stronger than its conjugate acid. Negatively charged nucleophile. Correct. So say OH minus, negatively charged. So this is always stronger base and a stronger nucleophile than water. Negatively charged nucleophile is always stronger than the conjugate acid. The conjugate acid is water here. Okay, therefore OH minus, it is a stronger base and a stronger nucleophile than water. H2O. Okay, H2O is the conjugate acid here. Now we can say, it's right to left to the periodic table, we can say, in the column, in the period, right to left across a row of the periodic table. What will be the trend here? Nucleophilicity increases as basicity increases. Okay, if you see the periodic trend here, that is across a row of the periodic table, right to left, if you see like this. Okay, now the nucleophilicity, it will increase as the basicity increases. Now we have this, say, CH3 minus, then we have NH2 minus. What will be the nucleophilicity and basicity here? OH minus, fluoride. So we know increasing basicity increases nucleophilicity, like this if you see. Okay, now right to left, this is the right to left. If you see like this, increasing basicity. So we have seen increasing basicity. Okay, increasing basicity, increasing nucleophilicity. Okay, so this is the point here. That is, right to left across a row of the periodic table, nucleophilicity increases as the basicity increases. Correct? Increasing basicity, increasing nucleophilicity. Now, there are certain cases here, steric effects, and nucleophilicity. Okay, I will just give an example. Because of the steric effect, the entire thing will change. So steric effects and nucleophilicity. So if you are having a compound like this here, say CH3, what is this? This compound is known as tertiary butoxide. Tertiary, TRT, we write here, then butoxide. Okay, tertiary butoxide, it is a stronger base compared to ethoxide. Interesting. So ethoxide is CH3, CH2, O minus. This is ethoxide. So now you compare, say tertiary butoxide, it is a stronger base. It's a stronger base means it will become a weaker, that basicity, if you see that, tertiary butoxide is a stronger base compared to ethoxide. Okay, now but the nucleophilicity, we are comparing the nucleophilicity here. So this ethoxide is it is a stronger nucleophile. That is, the tertiary butoxide, I will just write here, you should not get confused here. Okay, it is a stronger base. Stronger base compared to, this is our ethoxide here. Compared to ethoxide, this is a stronger base. That means ethoxide is a weaker base here. But now we can see, but ethoxide is a stronger nucleophile. That is the difference here. Weaker base, but stronger nucleophile, because it is against the general trend. Generally, we have seen strong nucleophiles are strong bases. Everything is same. Correct. But there are certain exceptions we have seen here. That is the weak base here, base becoming a strong nucleophile. Correct. So ethoxide is a weaker base, but it is a stronger nucleophile at the same time. Now tertiary butoxide is a stronger base, but a weaker nucleophile. This is the difference. Because of steric factors. This is the reason here. Okay, now in the case of tertiary butoxide, how will you write here? That is a methyl group here. O minus. Okay, this is our tertiary butoxide here. So the three methyl groups around the oxygen atoms, it will create steric hindrance. Okay, that is compared to ethanol, ethoxide is a weaker base, but at the same time it is a stronger nucleophile. The difference is being explained on account of steric hindrance here. That is, in the case of tertiary butoxide, the three methyl groups are there around the oxygen atoms here. Around the oxygen atom, it will create steric hindrance here. Okay, steric hindrance. So making it more difficult for the big bulky groups to attack. Okay, a is a tetravalent carbon atom. So bulky groups can, it will become difficult for them. That is the thing. The methyl groups around the oxygen atom, it is creating steric hindrance here. Because of the steric hindrance, it becomes difficult for the big bulky base, to attack That is why it is becoming a weaker nucleophile. That is the explanation being given here. Tertiary butoxide here. Steric hindrance, it decreases. Okay, steric hindrance decreases the nucleophilicity. So because it is a weaker nucleophile, the steric hindrance decreases the nucleophilicity of tertiary butoxide because of steric hindrance. Okay, but not the basicity here. Why? Because basis means it depend it all depends upon the affinity for the protons there. Okay, the bases, they pull off the small protons here. Protons are easily accessible protons here. Therefore, they are not affected rather by the steric hindrance, unlike other bulky groups here. Therefore, nucleophiles, it must attack here. What happens? A crowded tetrahedral carbon atom here. That is very difficult. So bulky groups decrease the reactivity. Okay, this is the bulky group here. Steric hindrance, is caused by these bulky groups here. Therefore, it will decrease the reactivity. Okay. Now, the sterically hindered bases, that are poor nucleophiles. Okay, you can generalize this thing. That is sterically hindered bases. They are poor nucleophiles. They are called, there is a word for that, non-nucleophilic bases. This is the word used for this. Okay, that is the sterically hindered bases that are poor nucleophiles, just like the tertiary butoxide here. Okay, potassium tertiary butoxide, I will just write here. They are called non-nucleophilic bases. An example, if you are asked to give, which is a non-nucleophilic base, here it is a, say, potassium tertiary butoxide, we can say here. Okay. That is a non-nucleophilic base here. So, a potassium tertiary butoxide, potassium, then we have this OC, CO minus, Ca3 thrice. Okay, this is the compound here. So, it is a strong non-nucleophilic base. Potassium tertiary butoxide. So, it is a strong non-nucleophilic base. Okay, because the steric hindrance, it decreases the nucleophilicity, but not the basicity. Basic point here. Okay, because the basicity determined by the reaction with a proton. Bronsted-Lowry base. Basicity determines, it determined by the reactivity with a proton here. So the bases are able to pull off the small, that is small protons, not bulky groups here. They are unaffected by the steric hindrance protons here. Okay, so nucleophiles must attack a crowded tetrahedral carbon. So the bulky groups decrease the reactivities here. Okay, because the nucleophilicity and nucleophiles and bases attack protons. What they attack? Bases are attacking a proton. Okay, but nucleophiles attack an electron deficient carbon atom, an electrophilic carbon atom here. Okay, that is a tetrahedral carbon atom, electrophilic carbon atom. So bulky groups find it difficult for them. That is why the reactivity is less, because of the steric factor, steric hindrance here. So potassium tertiary butoxide, it is a non-nucleophilic base. Correct? The reactivity is, as a nucleophile, is much less here. Steric hindrance here. Correct. Now, this is the nucleophile. It is simply an atom. It can be a functional group. Nucleophiles can be an atom, or it can be a functional group with one or more non-bonding electron pairs. Okay. Now this, it is willing to share that electron pair with a electron deficient or electrophilic atom in the substrate here. Okay. This is the nucleophile here. Okay. Now the strong nucleophile means, they are defined by the willingness to share that electron pair. Okay, so So the strong nucleophile, it can be defined by the willingness to share an electron pair here. Okay, nucleophiles, we can also be described in terms of the property as a basis that we have seen now. Okay, so when the good basis will be a good nucleophile and all these things we have discussed here now. Okay, I hope you have understood. So thank you so much.